Good morning, dear students, and once again, welcome back to our course. In the last lecture, we discussed in detail about the concept of different kinds of element which are normally used in case of network or a circuit, and basically, we came to know that depending upon whether the element is capable to supply energy or they are going to consume energy or store energy. Based on that, we can classify circuits element into two main domain. First one is called as active element and second one is called as passive element. When I say passive, that means they are either going to dissipate energy or they are going to store energy. When I say dissipate, example is resistor. When I say a kind of passive element which are capable to store energy either in the form of electric field or in the form of magnetic field. So based on that, we have capacitors and inductor. In the same way, in case of active element, a kind of element which are capable to deliver energy, so we can classify them into two main domain. First one is called as practical and second one is called as ideal. Now practical and ideal are nothing but again two type. We may have a practical voltage source, we may have a practical current source. In the same way, in case of ideal category, again we have two main domain. We may have ideal voltage source or we may have ideal current source. And then we also discussed another domain to classify circuit element based on whether their values are dependent on some other circuit parameters or they are independent. So based on that, we have four different types of dependent electrical circuit sources. We may have current controlled voltage source or we may have voltage controlled voltage source. In the same way, we may have current controlled current source or voltage controlled current source. And in the last lecture, we are solving numerical on voltage as well as current dependent sources if they are available in the circuit, how to solve those type of circuits. So let us continue with our sessions. So first in this, we are going to solve some more numerical on the calculations of dependent sources, and then we will start our today's topic, that is Kirchhoff's laws, which plays an important role in order to analyze a given circuit. And let me tell you one thing, that whatever the topic which I'm going to cover in today's lecture, again it is common for both electrical as well as electronics and communication engineering students, because circuit theory is common for both as far as the GATE syllabus is concerned. So let us start with our today's session. So here on this board I have shown a circuit where we have three different types of element. This is a voltage source of magnitude 10 volt. Then we have a resistor of ohmic value 2 ohm, and the current flowing through this resistor is I naught. And here we have a dependent source. Now the first thing is we have to identify which kind of dependent source is this, whether it is a voltage source or it is a current source. In the last lecture, I told you that how to identify dependent sources. The thing is that if we have a diamond shaped structure, then by default it is going to be a dependent source. Now we need to identify whether it is a voltage source or whether it is a current source. So how to identify that? The thing is that if we have a diamond shaped structure, and in that structure if we provide a fixed polarity like plus and minus, then this is going to be a voltage source. So definitely this symbol indicate a voltage source. Now we need to identify on what parameter the value of this voltage source is going to be depend, whether it is going to be controlled by a current in a circuit or whether it is going to be controlled by a voltage in a circuit. So from this we can easily identify what will be the nature of this voltage source. See, the magnitude of this voltage source is specified like 3 into I naught. So here this 3 is basically a parameter, a constant factor, and this I naught indicate that it is a current controlled voltage source. That means the moment we vary the value of this current, automatically the magnitude of this voltage source is going to be varying. And what is this I naught? This I naught is simply the value of current flowing through this 2 ohm resistor. So, but obviously this voltage source is going to be a current controlled voltage source. So this is very important. So whenever you have this kind of circuits in gate exam, first of all you have to identify whether the given dependent source is of voltage control category or current control category. And then once you have identified this, then we need to apply some circuit theory. We need to apply some laws. It may be law of conservation of energy, or it may be law of conservation of charge, to find out the desired answer. So I hope this point is clear to everyone. So in this particular circuit, we have three elements, out of which two are active. First one will be a voltage source of magnitude 10 volt. Then we have another active element, but of the kind dependent, which is nothing but a current controlled voltage source, and the magnitude is nothing but 3 I naught. And then we have a passive element of nature resistive, and the value is 2 ohm, and the current flowing through this circuit is nothing but I naught. And the objective is we need to calculate the value of this I naught. What will be the value of this I naught? Now, in order to calculate the value of I naught, what we need to do, we have to apply a simple law of conservation of energy. In the last lecture, or you can say the first lecture of this course, I told you that voltage is proportional to energy, because if you see the basic definition of voltage, it is nothing but energy per unit charge. So V is proportional to E. So in this particular circuit, because all the elements we can express in terms of voltage, we can easily apply law of conservation of energy over here. So how to apply that? So see here, the current flowing through this circuit is I naught, and the direction is in this particular way. So I told you that current always flows from higher potential to lower potential. So this is going to be a plus and this is going to be a minus. And suppose if you are interested to calculate what will be the value of voltage which is developed across this particular resistor, it is simply the application of Ohm's law, which is nothing but 2 into I naught. So 2 into I naught indicate the magnitude of voltage across this particular resistor. In the same way, when we move across this particular voltage source, which is nothing but a kind of dependent voltage source, again this is nothing but a voltage source where this point is going to be plus and this point is going to be minus. And then when we are moving through this voltage source, we are basically moving from negative to positive. So here we need to apply the concept of voltage rise or voltage drop. So in the last lecture, I told you that suppose we have an element, it may be anything, it may be resistor, inductor, capacitor, or any kind of active element. For example, let me indicate that by a general symbol like this. Suppose we have an element, and to this element, let us consider that the value of current is flowing in this direction, say I. I told you that current always flows from higher potential to lower potential. So this point is going to be plus and this point is going to be minus. Now suppose if I am interested to write the expression for voltage which is going to be developed across this particular element, and let us consider that the ohmic value of this element is say capital R. So how to write that? V is going to be equal to I, that is the current flowing through that element, multiplied by effective resistance or the ohmic value, that is nothing but R. Now the way I'm going to read this circuit, it may possible that I may read this circuit from left to right, or it may possible that I may read this particular circuit from right to left. So when I read this particular circuit from right to left, that means in the direction of current, I'm going to experience a voltage drop. So I can write this as minus I into R. Why it is negative? because when we are moving in the circuit in the direction of current, current always flows from higher potential to lower potential. So I told you that higher means 1, lower means 0. So we are basically going from 1 to 0. So we will experience a drop, and the drop is I into R. It may possible that one may read this circuit in the opposite direction. For example, from right to left. Then what will happen? It will experience a gain, because basically we are moving in the opposite direction of current, and when we are moving in a circuit in the opposite direction of current, we are basically moving from lower value to higher value. So we will gain, or we will experience a voltage rise. Then in that case, this is going to be plus I into R. So this sign convention you need to implement. So according to my sign convention, voltage drop is nothing but negative. That means when we are moving in the direction of current, and voltage rise is going to be positive when we are moving in the opposite direction of current. So this thumb rules you have to remember while solving this numerical. So once you have done with this, let me erase this so that we can solve this numerical, or let it be as it is. We have enough space to solve this numerical. Now see here. In this circuit, suppose I am moving in a clockwise direction, like this, in clockwise direction. So first I need to pass through this particular element, which is nothing but a voltage source. So I'm moving in a clockwise direction, that is from negative to positive. So I'm going to experience a voltage rise, because I'm moving from lower level to higher level. And what will the magnitude of that voltage? It is nothing but plus 10 volt. So here I need to write plus 10 volt. So basically I am here applying law of conservation of energy, because I am writing the entire equation in terms of voltage, and we know that voltage is proportional to energy. So here we have plus 10 volt. Then when we are moving across this particular resistor, so in this particular case current is flowing from left to right, and again we are moving in a clockwise direction. That means we are moving in the direction of current. So whenever we are moving in the direction of current, so here basically we are moving from positive to negative, so we will experience a drop. So here we need to write minus. And what will the magnitude of that voltage drop? It is simply the product of I into R. So here I need to write I naught into R. And then what about this? Again we are moving in the clockwise direction, that means in the downward direction. And here we are basically moving from plus to minus. So plus to minus means again we are going to face a drop. That means we need to take this as negative. And what will be the magnitude of this voltage source? It is simply 3 into I naught. So here we need to write 3 into I naught. And this is going to be 0. I hope this equation is very clear to everyone, because it is a fundamental condition. If you are unable to write this equation, then it is very difficult for you to solve numerical, especially in circuit theory. So the thing is that here simply I have applied law of conservation of energy, and I have applied this sign convention. Whenever we experience a voltage rise, I need to take that voltage as positive, and whenever we experience a voltage drop, I need to take that particular term as negative. So here we will experience a rise, that's why plus, and then in this case positive negative drop, so minus 2 into I naught, and again in this particular case positive to negative again drop, that's why minus. Now this is very simple. Here we have one equation and one unknown quantity, which is nothing but I naught, so we can easily solve this. So I can write this as 10 is equals to 3 plus 2, which is nothing but 5 into I naught. And if you solve for I naught, this is going to be equal to 10 by 5, which is going to be 2 ampere. So this is what the solution for this circuit. In the same way, suppose in this numerical, if they may ask to calculate what will be the value of this current controlled voltage source. So how to calculate that? See, the magnitude of this current controlled voltage source, suppose indicated by symbol V, is simply 3 into I naught. So first we have to calculate the value of I naught, and we got the value of I naught as 2 ampere. So I can write this as V equals to 3 into 2. So this is going to be equal to 6 volt. Why we need to write here as volt? Because it is by default a voltage source. So but obviously the magnitude has to be in volt. So the answer is 6 volt. So the current flowing through the circuit is I naught, which is nothing but 2 ampere, and the magnitude of this current control voltage source is nothing but 6 volt. So in this way we can solve the numerical on dependent sources if they are available in the circuit. Let us try to solve one more numerical. Suppose here we have a voltage source of magnitude say 10 volt, and here we are having a resistor of value say 2 ohm, and the voltage across this resistor is given to us, which is nothing but V naught, and somewhere over here we have a dependent source. Why it is dependent source? Because of its shape. It is diamond shape, that's why it is a dependent, and that too voltage, because here we have fixed polarity plus and minus, and the magnitude of this voltage source is given by 2 into V naught. So from this it is very clear that it is nothing but voltage controlled voltage source. Why it is called as voltage controlled? Because the magnitude of this voltage source is dependent on V naught, where V naught is the voltage across this particular resistor. And somewhere over here, let me erase this. Somewhere over here we have one more element, that is a resistor, and the magnitude of that resistor is 3 ohm. And here our objective is to calculate the value of V naught. What will be the value of this V naught? So how to solve this? Again, it is a very simple numerical. First of all, we need to assume some parameters over here. Let us consider that the value of current flowing through the circuit is indicated by symbol I. And because we have a independent source over here is 10 volt, that's why I have assumed that the value of current which is coming out from the positive terminal of this voltage source, and when this particular current is flowing through this 2 ohm resistor, it will experience a voltage, and because the current is from left to right, this is plus and this is going to be minus, so same sign is given in the numerical. And then the same current is flowing through this because all are in series combination, and the same current is flowing through this, which is nothing but I. So the moment we have a flow of current through this 3 ohm resistor, here we need to indicate the polarity. So this is going to be plus and this is going to be minus. Now why it is plus and why it is minus? The reason is very simple. I have assumed that the current is flowing in the clockwise direction, and current always flows from higher potential to lower potential. So here the voltage drop or voltage rise, that depends upon the way I'm reading this circuit, is something like this. But with respect to this diagram, when the current is flowing from right to left, here this is going to be plus and this is going to be the minus. Now let us try to read this circuit. Let us try to read the circuit in the clockwise direction and apply law of conservation of energy. So by applying law of conservation of energy, because V is proportional to E, first we have this element which is nothing but a 10 volt voltage source, and we are moving in clockwise. That means we are moving with respect to this particular element in upward direction. That means from negative to positive. So we will experience a rise, and the rise is of 10 volt plus 10 volt. Then when we are moving through this element in the direction of current plus to minus, we will experience a drop, and drop is negative. So what will be the magnitude of that particular uh, voltage? It is simply 2 into I. In the same way, when we are moving through this particular element, we will experience a voltage drop because we are moving from plus to minus. So it will be minus 2 into V naught. And then when we are moving through this particular element in the direction of current, we will experience a drop because we are moving from plus to minus. So drop. So drop has to be negative. So minus 3 into I, and this is going to be equal to 0. Now if you rearrange the terms, we can write this equation as 10 minus 3 and 2. Here it is going to be 5I, which is going to be equal to 2V naught. That this will be your equation number 1. Now to solve this equation, we have two unknown quantity. First one is I and second one is V naught. So mathematical thumb rule is that if you have two unknown quantity, minimum you require two equations to solve those unknown quantity. So what we need to do, either we need to replace this volt in terms of current, or we need to replace this current in terms of volt. So depending upon your requirement, you may apply any one of the logic and you can solve for I, or you can solve directly for V. Now see here, in this particular equation, let us focus on this element, only this element. Suppose if I am interested to write the voltage across this element, what will be the equation for voltage? It is simply V naught, which is going to be equal to a current flowing through that circuit multiplied by resistor. So from this I can write I is simply V naught divided by 2, or I can simply replace V naught as 2 into I. So what we are going to do, because our objective is to solve for V naught, so what we will do, we will replace this I in terms of V naught. So let this will be your equation number 2. So what we are going to do, from equation 1 and 2, I can write here as 10 minus 5. Now instead of writing I am going to write this I as V naught by 2, which is going to be equal to 2 times of V naught. Now this is very simple. We have only one equation, and that too in that equation we have only one unknown parameter. Now it is very easy to solve this. So if you solve this for V naught, I can write this as V10 equals to, this is supposed to be on right hand side, so it is going to be 5 by 2 plus 2 whole multiplied by V naught. Or if you further solve this, this is 4 then plus 5, that is going to be 9 by 2 is going to be equals to V naught. Or I can write here as V naught is 10 into 2 divided by 9, or it is simply 20 by 9 volt. So this is our final answer, 20 by 9 volt. So in this way we can solve numerical on circuit theory, in which we have a combination of dependent as well as independent voltage source. Now let us try to solve one more numerical from previous year gate exam. So this question was asked in gate 2015 for 1 mark, and the circuit is something like this. So here we have a current source of magnitude 5 ampere, and somewhere over here we have a 4 ohm resistor, and then again somewhere over here we have 4 ohm resistor, and then the circuit is something like this. Again we have one more resistor of value 4 ohm, and this is a dependent source. Now whether it is a current control or it is a voltage control, that we need to find out. See, this is arrow, that's why it is a current source. And the magnitude is specified like 2 into I. So it is going to be a current controlled current source. And what is I? So I is a current flowing through this resistor. So this is very important. And here our objective is to find the value of that voltage, I think. Let me check this. Okay, so here we have one more parameter, which is plus, and here we have minus, and this voltage is say V1, and our objective is to find the value of this V1. That means what will the voltage across this current controlled current source. So how to solve this numerical? Again, it is very simple. The thing is that, see, in this particular case, if you see the circuit very carefully, this element, this element, and this element all are connected in parallel. See, from the circuit it is very clear that these three elements are connected in parallel, and the moment they are connected in parallel, voltage will remain same. That means in the numerical it is given that this is V1, where V1 is the voltage across this particular current controlled current source. So same V1 is going to appear across this resistor, and the same V1 is going to appear across this particular resistor. So here we have V1, again here we have V1, and the same V1 is available over here. So mathematically, if I'm interested to write the expression for V1, I can write V1 as 4 into I. See, with respect to this particular element, what is going to be V1? V1 is simply the voltage across this resistor. And how to write that? It is simply the current flowing through that resistor multiplied by its ohmic value. So it is going to be 4 into I. Or we can write V1 as I into 4. Both are nothing but the same thing. I hope this is clear to everyone. In the same way, suppose, see, through this particular field, we have a current, and the magnitude of this current is nothing but 2I. So here we have a current of magnitude 2I. Now suppose if I'm interested to find out what will be the value of current flowing through this particular resistor, how to solve this? See, the current flowing through this resistor, suppose it is indicated by symbol say I1. So I can write here as I1 is simply V by R, where V is nothing but V1, because I am writing the equation of current flowing through this particular resistor. So what we need to do, we have to take a voltage across this resistor, and the voltage is V1 because all are connected in parallel, divided by the ohmic value of this resistor, and the ohmic value is 4. So we can write I1 as V1 by 4. So we know that the value of current flowing through this resistor is I, which is already given to us. The value of current flowing through this particular resistor is V1 by 4, or we can write this as, because we know that V1 is nothing but I into 4, so it is going to be equals to I into 4 divided by 4. So this 4 will get cancelled, and we know that value of I is going to be what? I. And we know that the value of current flowing through this particular circuit, or this particular, is nothing but what? 2 into I. And see here, this is nothing but a current source. So the main current flowing through this particular circuit is nothing but 5. So what we need to do? Here we need to apply law of conservation of charge. So whatever the charge which are coming in to the circuit, the net charge or the same charge is going to flow inside that particular circuit. So here I can write here as the main input charge or current, because current is proportional to charge. That's why we need to apply the concept of law of conservation of charge. So here this 5 is going to be equal to the current flowing through this particular resistor, which is nothing but I, then plus current flowing through this particular resistor, which is nothing but I1, and we know that I1 is V1 by 4, and V1 is nothing but 4 into I. So we can write I1 as again I, and then plus the current flowing through this particular branch, which is nothing but 2I. So here we need to write as 2I. So if you solve this, we can write I as 5 divided by 2 plus 3 plus 1, which is nothing but 4. So I can write I as 5 by 4. Now let us try to calculate the value of this V1. V1 is going to be equal to 4 into I, and 4 into what is I? I is simply 5 by 4. So this 4 will get cancelled, and we can find V1 as 5 fold. So in this way we can solve the numerical, and once you know the value of V1, you can easily calculate the value of voltages, or you can say current, across each and every element available in this particular circuit. The thing is that you should know how to solve this numerical, and here what we have done, first we have calculated the current flowing through each and every element, like what is the value of current flowing through this, what is the value of current flowing through this, and what will the value of current flowing through this. And then we have applied law of conservation of charge to solve the value of current first. Once we know the value of current, we can easily find out what will the value of that V1, where V1 is nothing but the voltage across this current controlled current source. So this was the question asked in GATE 2015 for 1 mark. Now let us discuss some more technical aspect related to the analysis of circuit theory. For example, if we have passive elements, and from the knowledge of our previous lecture, we know that basically the most common type of passive elements which are available in any electrical or electronic circuits are nothing but R, L, and then we have C. So how to find the equivalent resistance when they are connected in series or when they are connected in parallel? So see here, when we have two resistors, say R1 and R2, if they are connected in series, then what will be the equivalent? So R equivalent simply the addition of each individual resistance. So R equivalent is going to be R1 plus R2. In the same way, if you have two resistors in parallel combinations like this, like R1 followed by R2, and our objective is to find R equivalent. So here what we need to do, when two or more than two resistors are connected in parallel combination, we need to add by inversing them. So I can write here as 1 upon R equivalent is going to be equal to 1 upon R1 plus 1 upon R2. And if you solve this for R equivalent, it is like product into sum. So I can write here as R1 into R2 divided by R1 plus R2. So this you have to remember. In the same way, suppose if you have inductors, like two inductors, say L1 and L2, and suppose if they are connected in series combination, so L equivalent is going to be equal to L1 plus L2. While writing this equation, I have considered that the mutual inductance between these two are 0. Otherwise, the equations may get modified. In the same way, uh, if you have two inductors and they are connected in parallel configurations, where this is going to be L1 and this is going to be L2. So how to find L equivalent? Exactly the same like we have applied in case of resistors. So it is going to be 1 upon L equivalent is 1 upon L1 plus 1 upon L2, or we can simply write here as L1 into L2 divided by L1 plus L2. But in case of capacitance, the condition is exactly contradict. For example, if you have capacitors which are connected in series, say C1 and C2, so the C equivalent is, we need to add them in inverse configuration like this. The way we have solved two resistors or two inductors in parallel, the same logic we need to apply over here to find the capacitors when they are connected in series configuration. So it is going to be equal to C1 into C2 divided by C1 plus C2. And if they are connected in parallel configurations like this, where this is C1 and this is going to be C2, so C equivalent is going to be equal to C1 plus C2. So from this, what we conclude, when the resistors and the inductors are connected in series configuration, the net effective resistance or the net effective inductance is going to be increased because they are straight away adding. Whereas if the capacitors are connected in series configuration, the net effective capacitance is going to be reduced. In the same way, if two or more than two resistors or inductors are going to be connected in parallel, the net equivalent resistance or the net equivalent capacitance is going to be reduced. Whereas the case is exactly contradict in case of capacitance. That means if two or more than two capacitors are connected in parallel configuration, the effective capacitance is going to be increased because it is simply the addition of individual capacitance. So this is very important, and this uh, things you have to remember while solving numerical on circuit theory. In the same way, you should know what are the design parameters formulae to calculate the value of resistor, inductor, and capacitors, which is very, very important. For example, if you have a resistor, then how to calculate the value of that resistor if you know its dimension? Or sometimes these formulas are also called as dimensional formulas to calculate the value of resistor, inductor, and capacitors. So let us consider that we have a piece of metal having some finite length and having some finite cross-sectional area. Cross-sectional area is say A, and the length is say L. And let us consider that the resistivity of this particular material is indicated by symbol rho. So how to calculate the resistance of this material? So we can write R is equals to rho L by A. This is very, very important, where rho is the resistivity, and the resistivity of an element only depends upon the nature of that particular material. This is very important. Whereas resistance may depends on nature of material, it also depends on temperature, it also depends on length, it also depends on cross sectional area. But as far as resistivity is concerned, it only depends on the nature of material. That means once the material is same, it will always going to offer same value of resistivity at constant temperature. The moment we change the material, definitely the resistivity associated with that particular material is also going to change. So this is a kind of theory from on which there will be one question in previous gate exams, like which of the following factor decide the value of resistivity? And the options are, first one is length, second one is cross sectional area, third one is nature of material, and fourth one is all of above, or all of this. And the best answer is nature of material, because resistivity does not depends on length, it does not depends on area, it does not depends on you can say the physical dimensions. The thing is that it only depends upon the nature of that particular material. Once the material is same, the resistivity of that particular material almost going to be same for constant temperature. If the same question is asked like this, which of the following factor decide the value of resistance, then the answer for this particular question is all of this. Because in case of resistance, the value is depends on length, it also depends on cross sectional area, it also depends on the nature of material, and It may possible that in this particular numerical we may have the concept of temperature. So temperature is also going to be decided by both resistance as well as resistivity. Resistivity is also going to vary with respect to temperature. Resistance is also going to vary with respect to temperature. And now suppose if you are interested to find out how the resistance of a material is going to vary with respect to temperature. So there we have one parameter which is called as temperature coefficient of resistance, indicated by symbol alpha, and we can write here as R2, which is nothing but the resistance of a material at temperature T2 is going to be equal to R1, where R1 is nothing but the resistance of material at, say, temperature T1, in bracket alpha multiplied by delta T plus 1, where this delta T in this case is going to be equal to T2 minus T1, and this alpha is known as temperature coefficient of resistance. So from this mathematical formula you can easily calculate what will be the value of resistance of a material if you know the resistance of that material at certain temperature. The thing is that you have to apply this formula. And uh, what will be the unit for this resistivity? See, from this equation we can calculate the unit for resistivity. It is rho is equals to R into A by L. The unit for resistance is ohm. Suppose we specify all the dimensions in meter. So area will be meter square divided by length will be in meter. So this meter, the square will get cancelled, and the unit for resistivity is ohm meter. So this you have to remember. In the same way, we may have the formulas to calculate physical dimensions, parameters of inductor as well as capacitor. So, inductor is calculated like this: L is equals to n square mu A by L, where n indicate the number of turns available in that particular inductor, and mu indicate the permeability of the material, where A indicate cross sectional area and L indicate the effective length of that particular inductor, and the unit for inductor is Henry. In the same way we can calculate capacitance C, which is given by epsilon A by D, where epsilon indicate the permittivity, and this capital A indicate the cross sectional area. For example, if you have a parallel plate capacitors, like one plate is over here and another plate is over here, and suppose this is first point and this will be the second point, so this is nothing but the area A, and the distance between these two plates is indicated by symbol D, and the permittivity offered by a medium which is placed in between these two parallel plates is indicated by symbol eta. So this formulas you have to remember, and the unit for capacitance is nothing but farad. So these are very common, very basic, but they are very much crucial formulas to solve numericals on circuit theory. Now let us discuss the concept of Kirchhoff's laws, Kirchhoff's voltage law, and Kirchhoff's current law. But before that, let us discuss one of the most important topic, or you can say a simple terminology, what exactly a mesh is, what is the meaning of node, and what is the meaning of branch. Mesh are normally indicated by symbol M, node are indicated by symbol N, and branch are indicated by symbol B. So, what is the relationship between mesh, node, and branch for a given circuit, and what exactly the meaning of these three terms? So, what is mesh? Mesh is nothing but a smallest closed loop which is available in a circuit, which further cannot be divided into sub closed loop. So if you have a circuit, and in that circuit if you have a smallest closed loop, then that smallest closed loop is nothing but mesh. For example, let me explain you via a simple circuit. Let us consider that we have a voltage source, and then here we have a resistor, and somewhere over here we have another resistor, and somewhere over here we have another resistor, followed by a current source, and here we have one more resistor, and then here we have one more resistor, and the circuit is something like this. Let us consider this is a R1, here we have R2, here we have R3, and here we have R4, and here we have R5. This is a V and this is a I. So what is mesh? Mesh is nothing but a smallest closed path that is available in a given structure or in a given circuit. So in this particular structure, we have three closed paths. If you start from this voltage source, we will complete our path and reach back to voltage source through this. So this will be your first closed loop. In the same way, if we start our journey from this resistor, say R3, we will come back to resistor R3 like this. So this will be your circuit 2 or closed path 2. And then it may possible that we will start from this voltage source, say positive polarity. We will continue like this, and then through this circuit elements, we will again come back to this particular point like this. So this will be your circuit number 3. So in this particular structure, we have three closed paths. Now out of these three closed paths, one will be a closed path, but it cannot be treated as a mesh. Why? Because I told you that mesh is nothing but a kind of closed path which cannot be further sub-classified into closed path. That means it is the smallest closed path available in a circuit. So here if you see the closed path 1, it is the smallest closed path. It cannot have further closed paths in it. In the same way, if you see closed path number 2, it is the smallest closed path. It cannot have further sub-closed path in it. So here in this particular circuit, we have two mesh. Now let us try to identify what is node. Node is simply a junction or a terminal in a circuit where we have a combination of more than two or more than one circuit element. So what is node? It is nothing but a point or simply a junction in a circuit where we have a combination of two or more than two circuit elements. So that is nothing but node. For example, in this particular uh, figure or circuit, let us try to find out how many number of nodes are there. See, this is going to be one node. Why? Because it is a point where we have a combination of two circuit element. First one is the active voltage source followed by resistor R1. So this is your first node. In the same way, this is going to be another node because at this particular point we have a combination of three passive element R1, R2, R3. So this will be your second node. In the same way, this is going to be the third node, a combination of R2 followed by current source I. So this will be third node. In the same way, this is going to be the fourth node. Why? Because a combination of R5 followed by current I. So this will be the fourth node. And here we have fifth node, which is a combination of R3, R4 and R5. And then here we have the sixth one, which is a combination of voltage source V followed by resistor R4. So this is going to be the sixth node. So in this circuit, we have total 6 nodes, which is very important. 1, 2, 3, 4, 5, 6. Now let us try to identify or discuss what is the meaning of this branch. Branch are nothing but simply the elements which are available in the circuits. जितने भी elements आपके circuits में available रहेंगे, those you can treat as branch. Now in this particular structure, let us try to find out how many number of elements are there. See, in this case we have a voltage source. This will be your first element. Then we have passive element like R1, R2, R3, R4, and R5. So we have five passive elements: one, two, three, four, five. So five passive elements, and then we have one more active element, which is nothing but a current source. So here, total number of elements available in this particular circuits are nothing but 1 plus 5 plus 1. 1 will be your voltage source. Then we have five passive elements in the form of resistors R1, R2, R3, R4, and R5. And then we have one active element in the form of current. So if you add 5 plus 1 plus 1, it is going to be 7. So in this case, because we have 7 element, that's why the branches available in the circuits are nothing but 7. This is very simple. I hope this is clear to everyone. How to identify mesh, how to identify node, and how to identify branch. Mesh are nothing but smallest closed path available in a structure which cannot further subdivided into closed path. What is node? It is nothing but a point or a junction in a circuit where we have a combination of two or more than two circuits element. It may be active, it may be passive, it may be active active, or it may be a passive passive. And what is branch? It is simply how many number of elements are available in a given structure or a circuit. It may be active or it may be passive. The thing is that just we need to count them one by one. Now let us try to write a mathematical relationship between mesh, node, and branch. So how to write this? So see here, in this equation we have mesh like 2, we have node like 6, and we have branches like 7. So I can write here as mesh is equals to uh, see, mesh is nothing but 2, which is going to be equal to branch minus node plus 1. So branch minus node plus 1. So in this case, how many number of branches are there? We have 7 branches. And how many number of nodes? We have 6 node, and then we need to add 1, which is in the formula itself. So if you try to find out 7 minus 6, which is going to be 1, 1 plus 1 is nothing but 2. See, the same value we are getting. So the relationship between mesh, branch, and node is nothing but mesh is equals to branch minus node plus 1. This is very, very important. And this is for all electrical circuits or network. Mesh are always going to be equals to b minus n plus 1, where b indicate branch, n indicate node, m indicate mesh. So this is very important. So once we have gone through this, now discuss the concept of KVL and KCL, or simply Kirchhoff's law. Kirchhoff's law or Kirchhoff's laws. Sometimes they are also called as Kirchhoff's first law and Kirchhoff's second law. So we have Kirchhoff's current law, and here we have Kirchhoff's voltage law. Kirchhoff's current law is also called as first law of Kirchhoff's, and Kirchhoff's voltage law is also called as second law of Kirchhoff's. Sometimes Kirchhoff's current law is also known as law of conservation of charge, because ultimately we are dealing with current, and we know that current is proportional to charge. That's why Kirchhoff's current law is also known as law of conservation of charge. Whereas in case of Kirchhoff's voltage law, we are trying to deal with voltage, and we know that voltage is proportional to energy. That's why Kirchhoff's voltage law is also known as law of conservation of energy. Here we have law of conservation of charge, and here we have law of conservation of energy. This is very, very important. Now let's try to analyze what will be the statement for Kirchhoff's current law and what will be the statement for Kirchhoff's voltage law. According to Kirchhoff's current law, at any node or at any junction, summation, or you can say algebraic summation of incoming current as well as outgoing current are always going to be zero. That means if you have a node and at that particular node or at that particular junction, if you have say n number of branches, in this case I have shown 5 branches, and to those branches, if you have say some incoming current or say outgoing current I3, I4, or say I5, so here I can write incoming current is nothing but I1 plus I2. Why they are called as incoming current? Because if you see the direction of those current, they are approaching towards the junction. That's why they are called as incoming. In the same way, if you are trying to calculate outgoing current, it is going to be equal to I3 plus I4 plus I5. Or according to Kirchhoff's current law, I can write incoming current is always going to be equal to outgoing current. So what is incoming current? Here incoming current is I1 plus I2, which is going to be equal to outgoing current, which is nothing but I3 plus I4 plus I5. Or I may shift this entire outgoing current on left hand side. So what will be? The equation is, it is going to be I1 plus I2, then we need to take minus of I3 minus of I4 minus of I5, going to be 0. Or I can write here as this I1 plus I2 as summation of incoming currents. Then if I take negative sign as common, so I can write this equation as summation of all outgoing current, which is going to be 0. And this is what the statement for Kirchhoff's current law. Kirchhoff's current law state that at a node or at a junction, summation of incoming current and the summation of outgoing current are exactly same, or if you take the algebraic sum, they must be always going to be 0. And while applying Kirchhoff's current law, we need to apply a simple sign convention that if you take incoming current as positive, you have to assign opposite sign to outgoing current. Then in that case, outgoing currents are going to be negative. Or you can make a reverse. If you assume that all incoming currents are negative, then in that case, all outgoing currents are going to be positive. So this is what the concept of Kirchhoff's current law. So Kirchhoff's current law is also known as first law of Kirchhoff's for circuit theory analysis. Sometimes Kirchhoff's current law is also called as law of conservation of charge, because we know that current is proportional to charge. And here we are writing the mathematical equation in terms of current. So I can easily make a correlationship between current and charge. So that's why this law is called as law of conservation of charge. And the statement is algebraic sum of current at any junction in a circuit is always going to be 0. Condition is that we need to apply proper sign conventions to the incoming current and outgoing current. If you take incoming current as positive, outgoing current is going to be negative. Or if you take outgoing current as positive, the incoming current is going to be a negative. This is very important. Now let us try to discuss the statement for Kirchhoff's voltage law. It is very simple. As I told you that Kirchhoff's voltage law is also known as law of conservation of energy. So according to this particular law, or second law of Kirchhoff's, in any closed path of a circuit, the algebraic sum of voltages, it may be a voltage drop or it may be a voltage rise, are always going to be 0. So this is what the statement for Kirchhoff's voltage law. So let us try to analyze this circuit, or let us try to identify what exactly the meaning for Kirchhoff's voltage law. For example, if you have a simple circuit like this, in which I have connected some elements like this, let us consider that the magnitude of this voltage source is say V, and the magnitude of these elements are R1, R2, and R3, and let us consider that the value of current flowing through the circuit is I in clockwise direction. Now, as I told you that the moment we have a closed path, we have a potential difference, there will be a flow of current through that particular path, and the current is indicated by symbol I. The moment we have a flow of current, it is always flows from higher potential to lower potential. So let us consider that this point is going to be plus and this point is going to be minus, and the magnitude of the voltage developed across this element is V1. In the same way, the same current is flowing through R2 in downward direction, so this is plus and this is going to be minus, and let us consider that the magnitude of that voltage is V2. In the same way, the same current is flowing through R3 from right to left, that's why this is going to be plus and this is going to be minus, and the voltage developed across this element is say V3, and then we have the same current coming back to the source, which is nothing but voltage. Now let us try to write a mathematical equation. Let us try to read this particular circuit in clockwise direction. So I am reading this circuit in clockwise direction, and I already told you that according to my sign convention, I follow voltage drop as negative and voltage rise as positive. Voltage drop means we are moving in the same direction of current. Voltage rise means we are moving in the opposite direction of current. That means voltage drop means positive to negative. Negative. Voltage rise means negative to positive. This is very important. So once you are clear with this, it is very simple to write the mathematical equation. So starting with terminal of voltage source V, I can write here as, when we are moving through this particular element, negative to positive, because we are moving in clockwise. So negative to positive, we are experiencing a rise in voltage. So this is going to be plus V. Then through this element, left to right, because we are moving in clockwise, left to right, left is plus, right is minus. So positive to negative, we are moving in the direction of current, we will experience a drop. So it is going to be minus I into R1. In the same way, when we are moving through this, again we are going to experience a drop, positive to negative in the direction of current. So minus I into R2. In the same way, when we are moving through this element, again we will going to experience a drop, positive to negative. So minus I into R3. This is going to be equals to 0. Or I can write this equation as V, if you take minus as common, or you can, yeah, if you take minus as a common, we can write this as I into R1 plus I into R2 plus I into R3 in bracket going to be equal to 0, whereas this is the summation of voltage drop. So I can write this equation as VR, which is nothing but voltage rise, minus summation of all voltages drop going to be equal to 0. This is what the equation of Kirchhoff's voltage law. That means if you take the algebraic sum of voltage rise and voltage drop available in any closed path of a circuit, it is always going to be equal to 0. Or this we can write as voltage rise is always going to be equals to the summation of voltage drop. Or in general, I can write here as summation of voltage rise is always going to be equals to summation of voltage drop. The condition is that we need to apply proper sign convention, and the proper sign convention is we need to take opposite sign. If you define voltage drop as negative, then in that case voltage rise has to be positive, or you may take voltage drop as positive, then in that case voltage rise has to be negative. So if you apply this sign convention in any closed path of a circuit, the algebraic sum of voltages, whether you take voltage rise or you take voltage drop, is always going to be equals to 0. And because here we are writing this equation in terms of voltage, and we know that voltage is proportional to energy, so basically we are trying to say that whatever the energy which you are supplying to that circuit, the same energy is going to either dissipate or store in various elements of that particular circuit. That's why Kirchhoff's voltage law is also known as law of conservation of energy. This is very, very important. So this is what I have decided to to cover through this particular session. So in today's session, we discussed first we solved some numerical based on if we have dependent sources available in the circuit, then we solved some uh, previous year gate numerical based on dependent sources calculations. Then we discussed the fundamental aspect of what exactly resistors, inductors, and capacitors, what will happen when they are connected in series parallel combinations. And then we discussed the concept of mesh, branch, and node, and we discussed a mathematical relationship between these three parameter. And then we have discussed the concept of KVL and KCL. Thank you.